Okay, so we're going to be looking at a voltaic cell problem where we don't have it in cell diagram form, but instead we have it in just a diagram or a picture. So we're going to say that the everything's at standard conditions, so we're going to have 1 atm and 25 degrees Celsius, and we're going to have 1 molarity for our concentrations. And so our first question is going to be, what is the total E cell? And we're going to be using our standard potential list over here for that. And I know that's hard to see, so let's just rewrite the ones we need. But first we need to see what our metals are going to turn into. And since we know that sulfate ions have a -2 charge, we know that our metals in an aqueous solution, they're going to have a +2 charge. So let's go ahead and find those reactions, and here's what these half reactions are going to be. Now, we need to keep in mind that these are both in reduction format. Well, we need one to be a reduction reaction and one to be an oxidation reaction. And we choose which one is going to be which by taking the most positive reduction action and keeping that as our reduction action. So in this case, that's going to be our copper reaction. So we can go ahead and label them both now as oxidation and reduction. And now with our zinc, it's not in the right format because that's still in reduction format. So we need to flip the equation around and change it into oxidation. And with that, we also have to change the charge from -0.76 to +0.76. So now we can write our equation, which is E cell equals the E of reduction and the E of oxidation. And we can plug in our values and we get our answer. And we need to keep in mind that our standard potentials are always going to be in volts. So our answer is 0.92 volts. Now for the next question, we're going to see which is the anode and which is the cathode. Now we can refer to our previous work and see that we have our reduction and oxidation half reactions labeled. Now there's this great phrase called an ox-red cat, and that helps us remember that anode is going to be where the oxidation occurs, and the cathode is going to be where the reduction occurs. So we now know then that our copper is going to be our cathode and our zinc is going to be our anode. And this is really helpful because this isn't like cell diagram form where the order tells us. You have to actually pay attention in a diagram because the anode and the cathode could be on either side. Now for our third question, we're going to have what is the balanced net ionic equation. So again, if we look at our previous work, we already wrote out the half reactions. Now to get the balanced net ionic equation, we add these two together. So we're going to take both of these equations and write them again, and we're going to put them to where we can add them. Now our electrons both cancel out, so we're going to write what's left over now to get our balanced net ionic equation. And that's our answer. So now we're going to go to number 4, which is which direction are the electrons flowing? And so we need to keep in mind that the which side is the cathode and which side is the anode. And our copper is our cathode and our zinc is our anode. So we also need to know this important fact, which is the fact that electrons travel from anode to cathode. And so because of that, we know that the reaction in this case, in this reaction, the electrons are going to be flowing from right to left, as you can see in the picture, as they flow from anode to cathode. And an easy way to remember this is that they flow from anode to cathode or from A to C. So that really helps you remember that. I hope you understand these problems now.